Now we review some classical interactions of light with material and resulting permittivity and refractive index. Lorentz model is one of the most common models for interaction of light with matter. It is based on interaction of two charges. These charges can be an atom with positive nucleus and negative bound electrons. It can be a molecule or a pair of ions. In this model, omega 0 is the resonance frequency of the bound charge and gamma is the damping factor of the bound charge resonance. Electric field of light works as a driving force and electromagnetic attraction as restoring force. For this system, we can write a classical force balance equation, which is a second-order differential equation. This leads to complex permittivity function. In case of several resonances, we can sum all their contributions. The details of the derivation can be found from many basic optics books, and we are not going into details here. Permittivity, according to the Lorentz model, applies especially well for gases, but it can be used with solid materials as well. In this case, materials are described as electrons bound into nucleus. In this model, omega 0 is the resonance frequency, epsilon infinity is high frequency limit of permittivity, F is oscillation strength of resonance, gamma is the damping factor of the resonance, and omega p is a so-called plasma resonance frequency, which is related to density of charges. Plasma frequency plays a significant role in metals, highly doped semiconductors, and plasmas, as we shall later see. Here's an example of permittivity and refractive index as function of frequency or wavelength. At resonance, we observe rapid change in both real and imaginary parts. The loss is highest at resonance, and far away the permittivity tends to the high frequency limit. Refractive index is square root of the relative permittivity. Its shape is very similar, as you can see. If we think about solid materials, we know that their atomic resonances often take place at ultraviolet wavelength range. Therefore, as a crude rule of thumb, the refractive index is increasing towards UV and its loss is increasing simultaneously. Drude model is a modification of the Lorentz model. If the material has no specific resonances, but interaction of light takes place with free electrons, we can neglect the resonance term. This model still has some damping, which is a result of collisions of the free electrons with nucleus. This damping results in small complex part of permittivity. Below is an example how the permittivity and refractive index look like as a function of frequency and wavelength. One important observation. Real part of permittivity is negative below the plasma resonance frequency. Later we shall see that this feature enables special guided modes called surface plasmon polaritons. When the respective refractive index is calculated, we observe refractive index below 1, which is connected with large imaginary part. It means that optical loss is high. Trude model is often used to model metals. As we see from the refractive index, the material is opaque at low frequencies and has high loss, but it becomes transparent at high frequencies meaning ultraviolet wavelengths. If carriers have no damping, for example in dilute ionized gas such as in plasma, we have a model for free electron plasma. In this model, damping is completely neglected, since there is only few collisions of the free electrons with the nucleus due to dilute material. In this case, imaginary part of permittivity is completely absent, but it is negative below plasma resonance frequency. Refractive index is 0 for negative permittivity, and large imaginary part shows high optical loss. This also indicates high reflection from plasma at long wavelengths, but plasmas are transparent at short wavelengths and high frequencies. We can also combine different models. For example, several metals follow well a so-called Trude-Lorentz model. In this case, we have both bound and free electrons. Permittivity and refractive index for silver are shown in the figure. This figure is typical for noble metals. Real part is below 1 and loss is high. Later we see that such refractive index supports a special class of waveguide modes called surface plasmon polaritons. Direct simplification of dielectrics with negligible loss is given by the Sellmeier model. It is essentially a Lorentz model when the damping term is neglected. It describes low-loss dielectrics very well. The most famous example is refractive index of fused silica. Its refractive index follows Sellmeier equation well from near UV to infrared. It is especially suitable in the telecom range around 1550 nanometers for predicting dispersion of optical fibers. Fundamentally, this model is not physically valid since it neglects loss near the resonances. In general, refractive index and loss depend on each other through the so-called Kramers-Kronig relations. This means that loss induces dispersion, and dispersion is a sign of loss in the material.